this webinar. Thank you for organizing this webinar. So today I would like to introduce about some of the latest technologies that have been brought by Evident Microscopy in the field of confocal microscopy and super resolution. As you know, super resolution microscopy is now is part of the current trend. However, there are different kinds of super resolution techniques that are available in the industry. Each super resolution microscopy comes with its own advantage, benefits, and limitations. I don't call it as a disadvantage. So each and every technique addresses some of the issues of the conventional confocal microscopy technique. While doing so, it has got its own limitations. So it is not the final solution for all imaging requirement. So coming to the basic requirement of any confocal microscopy, as you know, confocal microscopy is considered to be the gold standard for fluorescence imaging. It gives you excellent signal to noise ratio, better resolution, and it helps us to perform multi-channel, multi-dimensional image acquisitions. However, when you are performing these, there was a limitation in confocal microscope. The resolution was always limited to around 230 to 250 nanometers. That means if you want to see molecules that are smaller than 250 nanometer, confocal was not the solution. So there were different techniques that came into existence in the field of microscopy. One was called as SIM, or structured illumination based microscope, that gave a resolution of around 120 nanometer. Other one was called PALM. Other one was called STED. So they were giving a resolution of around 20 to 50 nanometer. So nowadays, like, you are getting a super resolution microscope that can even give a resolution of up to 2 nanometer, which is considered to be the best in the industry as of now. However, live cell imaging is also has become an integral part of biological science imaging, where people wants to image live cell with the super resolution requirement. So in addition to the spatial resolution that we are currently discussing in terms of nanometer in HY, spatial resolution is not only the requirement of live cell imaging. Live cell imaging also needs temporal resolution. That means how fast you can image. But if you are imaging faster, you should also retain enough signal to noise ratio. You should have enough signal. You should have lesser noise, and the resolution should not be compromised.
Sorry to interrupt you, sir. Are you moving your slides?
No, I'm not moving. I'm just giving a basic, brief introduction. Okay.
Okay.
So the first one what I'm showing you is a confocal microscope, which was a gold standard, was a point scanning confocal microscope. The second one was addressing some of the temporal resolution limitation of the point scanning confocal microscope, called spinning disk confocal microscope. Both these microscopes are confocal in nature, adhering to the basic phenomena of confocal, giving you wonderful signal to noise ratio, optical sectioning capability. Confocality was well restored. However, point scanning confocal microscope had its own limitation. So when you see a confocal microscope, what actually it does is, so it addresses one of the basic limitation of fluorescence imaging. If you see a sample of a small bead-like structures, it will never be seen as a bead. And because of a phenomena called diffraction, it creates a pattern called airy disk pattern. And this airy disk pattern, if they are together at a distance of less than 250 nanometer, they overlap and create a blurred image. This is one of the major disadvantage of a conventional wide field fluorescence microscope that was being used from several decades with a camera or imaging. How do you avoid this one? By introducing a laser instead of a mercury arc lamp or a LED light source. Instead of illuminating multi-point, we illuminate only one point at a time, avoiding overlapping of the points or the airy pattern or airy disk. So you are sequentially imaging point by point. So that's why you get a sharper image in XY. However, this laser was penetrating deeper into the tissue or the cell, multi-layer cell. So the major issue of getting out of focus light was not addressed. So in order to address, or in order to block the out of focus light, a pinhole or a confocal aperture was introduced at the conjugate plane, which blocks the out of focus light allows only the light that is passing through the confocal plane or the conjugate plane or the focal plane. So in this particular case, if you see here, this is my focal plane. The light or the image which is emanating from this particular point is passing through the pinhole. So that means the aperture size plays a major role in deciding the confocality. Anything which is below is considered as out of focus light, it is blocked. Anything which is above, it is also considered as out of focus light, which is also blocked. You get a sharper image just because of placing a small aperture and managing the aperture to the point spread factor. That's how you generate a point scanning confocal. Since you are using only one point laser here, so you have to scan all across the specimen and generate an image. So it is a time consuming process because these lasers are the point light source. It has to hit each and every point, and you should spend enough time to excite your fluorochrome on the specimen, and the emission which should be coming should be sufficient enough to form an image, because now you are collecting the emission from only one plane. So there will be substantial reduction in the amount of light that is reaching the detector, because you are placing a pinhole. The pinhole blocks the out of focus light. You are currently collecting only one particular optically sliced plane, and your amount of signal that is coming is lesser. So that means you cannot move faster. You need to spend enough time at each point, which we call it as a pixel dwell time, or in other words, we call it as exposure time. The amount of time that laser exposes onto the specimen should be enough to give you enough signal. But however, since it has to scan point by point, it cannot spend more time on each point. If you are using a conventional wide field fluorescence microscope, a camera probably used with an exposure time of 150 to 200 milliseconds or up to 500 milliseconds. But this camera is a multi-array detector where you have multiple pixels. You will be collecting all the pixels at one go of 300 milliseconds. You will get an image of the entire sample. However, in this particular point scanning confocal microscope, you have to excite point by point, so it takes a lot of time. So the exposure time, not what normally we can expect, is somewhere around few microseconds at each point. So in order to complete an image of the entire 512 by 512, it takes several seconds to give a respectable signal to noise ratio and a energy and an image. So confocal was a wonderful tool, but speed was only 7 to 10 frames per second because you have a galvo scanner. However, so in order to improve, there were new scanners were introduced called resonant scanners, and these resonant scanners were a wonderful tool for high-speed imaging. The exposure time or the pixel dwell time that was exciting your specimen at each point has been reduced to nanoseconds. That means from microseconds to nanoseconds. The amount of signal that you are collecting to the detector was also reduced to a larger extent. The signal to noise ratio was affected. The detector that we are using currently with the confocal microscope is not the conventional camera, which is a multi-pixel detector. Now, since you are exciting only one pixel at a time with a point light source, your detector is also a point detector called photomultiplier 2. With the minimal amount of signal that you are collecting, photomultiplier was able to amplify the signal by collecting an external voltage and thereby enhancing the signal. That's why we call it as a point detector or a photomultiplier tube, where it collects the signal from each point and it amplifies this electrons and finally convert it into a digital information. So introduction of the resonance scanner, though, helped us to get a faster imaging, the signal to noise ratio was compromised mainly because of the pixel dwell time or the exposure time of the laser is nanoseconds. It reduced to nanoseconds. And the sensitivity of the PMT that we are currently using is somewhere between 30 to 50%. That means every 100 photon coming from the specimen, only it could convert 30 to 50 of the photons into an image. So there was a greater amount of loss in the point scanning confocal microscope because of the poorer detector. Compared to the conventional camera that we use in the wide field fluorescence microscope, so the quantum efficiency or the sensitivity can range from 70 to 90%. That means it has an ability to collect more signal given an opportunity to collect the signal from the specimen. So though it was considered camera was a wonderful tool for high speed, high sensitive imaging, but it cannot be used for point excitation source. So the other disadvantage of point scanning confocal microscope is you had a limited resolution. So you can either keep it for 512 by 512, 1K by 1K, 2K by 2K. At the max, you can probably go for 8K by 8K. But if we have to scan so many pixels, it takes a lot of time. So though it has an ability to image at a higher resolution, it was compromised because if you want to visit 8,000 pixels, it takes several seconds or minutes to complete one image. So sensitivity, as I told you, like it was only 35 to 45% earlier. Like nowadays, latest detectors are coming, which can even go up to 50 to 55%. So then what else? What should we do? Like if you want to achieve a higher speed without compromising the sensitivity. So a new technology was introduced called spinning disk confocal microscope. So as you know, the limitation of the point scanning confocal microscope was single point laser had to scan. If you had to have multiple point scanning illumination, then you have to make sure that like it has got enough distance so that it will not overlap. The airy disk will not overlap. So point scanning confocal microscope was replaced by a multi-point scanning confocal microscope called spinning disk confocal microscope, where a disk will rotate at a speed of 4,000 RPM with thousands of pinholes are there engraved on the spinning disk, and it allows the light to pass through with it showers multiple beams of light onto the specimen without overlapping each other, and it rotates and makes sure that the sample is illuminated throughout the specimen. When you are illuminating, so you should also make sure that you will be collecting this information pixel by pixel. Now, since you have a multi-pixel illumination option, you should be able to easily take the advantage of multi-pixel camera. So you can switch over from a conventional photomultiplier tube or a point scanning detector to a multi-pixel camera because they are more sensitive. Signal to noise ratio is better. Pixel size is bigger, dynamic range, or it can collect more photons. So we could have used all the advantage of a camera. How does a point scanning confocal microscope works? So now you have placed pinholes on a disc, and the distance between these two pinholes are made in such a way that no two airy discs will overlap here. The first airy disc is here, second airy disc is here. In between there is a space, so this airy disc will never overlap, so that you will be getting a sharper image. And the laser will pass through this disc, and it makes multiple beams hitting the specimen, and immediately the emission will come back and passes through the same pinhole and making sure that you are getting a confocal image. That's how a spinning disk confocal microscope works. But this was first introduced by NIPCO spinning disk, so it had its own limitation. Now coming to the point scanning confocal microscope, you had to point by point scanning. Now what you are doing is you illuminate multiple points and collect it together with the camera. So, however, there was a limitation in point scanning confocal microscope, in the spinning disk confocal microscope. Since we were using a pinhole, the lasers that were passing through the pinhole was being blocked because the laser light will pass through only the pinholes. The rest of the region it was blocked. This was one of the limitation of the NIPCO disc-based spinning disk confocal microscope, where you used to lose a lot of amount of light. So of late, what Yokogawa, a Japanese company, did is they introduced a micro lens which acts as a funnel, and now it collects all the lights together, focuses it onto the specimen with a higher intensity. Now you have a better light efficiency. Even the laser power is lower, it collects all the laser beam and makes a sharper beam and concentrates, and it brings down a sharper point of light onto the specimen. So initially the light, the excitation light was broader, and it became a small point light source, and it was passing through a second disk, which will in turn deliver the light onto your specimen. The first disk was called as the micro lens based disk. Second disk was the conventional NIPCO disk, and each pinhole will have a micro lens delivering high intensity into the specimen. What next? So now you have, this is the conventional spinning disk with a NIPCO disk, and this is a Yokogawa dual disk technology with a micro lens. So the excitation efficiency was only 1 to 2%. Here the excitation efficiency was 70%. That means you had to literally have a high laser power to have enough excitation onto the specimen with this NIPCO disk whereas the Yokogawa-based microlens-based spinning disk would have excelled the excitation efficiency by 70% just by having a microlens on the second disk. Now, how do you acquire an image? Now, this is the microlens-based disk. This is the second disk. Laser will come from the top and it passes to the second one, and then emission will go back. When the emission will go back, it passes through the pinhole. You place a dichroic mirror or a beam splitter that reflects the emission towards the scanner, and that's how you can connect an image. So you place a beam splitter, the beam splitter will collect the information on a conventional camera, and this camera is now high sensitive. It has an ability to collect up to 95% of the signal. With the latest technology called back illuminated scientific CMOS camera, can give a frame rate of up to 90 frames per second and a quantum efficiency of 95%. So sensitivity is high, frame rate is high, and these cameras are Peltier cooled to -30 degrees, so it can give excellent signal to noise. So by doing this, and what we have done is we have come over the problems of the issues of point scanning confocal microscope for imaging only one point at a time. Now we have multiple points to excite. And now we have improved the excitation efficiency by incorporating the dual disc technology with the microlens. The excitation efficiency has increased. Since we are doing multi-point imaging, so we can easily collect the information with a better detector, that is scientific CMOS camera, compared to the conventional photo multiplier tool that had a sensitivity of only up to 35 to 40%. So fine, we have achieved a better frame rate. Let's just have a small video. It works. If you see, this is the spinning disk confocal microscope. I'll just switch over to this one. See, this is the wide field fluorescence microscope where the LED light or the mercury arc lamp was used. Entire sample was illuminated. You get a blurry image because there is no pinhole. You were using a sensitive camera, but the pinhole was not there. Later on, a spinning disk confocal microscope with microlens was used. Multi-beams was introduced. And then you are getting a sensitive camera. Now you are gentle towards your specimen, but you are still getting an optical section because you have a pinhole. And that's the difference between conventional wide field fluorescence microscope and the spinning disk confocal. So the spinning disk confocal microscope has helped us to address the issues of point scanning confocal microscope and take the advantage of the wide field fluorescence microscope. Now you have a solution for fast, high-speed, multi-point imaging, multi-point excitation, and multi-point emission connection. The advantage is faster image capturing, improved image quality due to the higher signal to noise ratio, lesser photo bleaching and phototoxicity because you are using a high sensitive detector here. The cameras that were being earlier used called EMCCD cameras, now it has been replaced by scientific CMOS cameras, which has an ability to go up to 95% quantum efficiency. Pixel sizes are smaller than the EMCCD camera, and it gives you better spatial resolution, high speed of up to 100 frames per second, and better sensing. Just some examples like how fast the imaging can be done. A cell division can be captured in real time with a better sensitivity. So you can do vesicle tracking. You can do exocytosis and endocytosis imaging. You can do photo activation, photo manipulation experiment. All these things are done at a better. So spinning this confocal microscope has become a tool for live cell imaging. Okay. Now the question is, so we have achieved the major goal of getting a confocal microscope without compromising the sensitivity and speed. But the era is not there. The era is now moving to super resolution. So the limitation of confocal microscope was only resolving up to 230 to 250 nanometer. But there are techniques that are available in the industry which can even resolve up to 20 to 30 nanometer or 100 to 120 nanometer. So people started questioning, can we achieve a speed with the resolution? Because most of these super resolution techniques, they were giving excellent resolution, but the temporal resolution was always compromised. None of these super resolution microscopes were giving a resolution of more than 15 to 20 frames per second. But the demand was to achieve a better spatial resolution and temporal resolution. So Yokogawa came out with a new technique called super resolution by optical reassignment, where they could image at a resolution of more than conventional confocal. So if you look at this one, this is a conventional wide field fluorescence microscope, gives you a resolution of 250 to 300 nanometers. Confocal enhances the signal to noise ratio, thereby improving the signal to noise ratio and resolution. But this is a diffraction limit. So these are some of the techniques that were available. SIM is called structured illumination, that was giving you around 120 nanometer, 2 times improved to compare to the confocal microscope. If confocal is 250 nanometer, a SIM would have been given 120 to 130 nanometer. STED was giving 50 nanometer, and single molecule localization microscopy was able to do a localization precision of 10 to 15 nanometer. If you look at broadly, you can configure it into different. So this is your laser scanning confocal microscope. If your XY resolution is around 180 to 250 nanometer, Z resolution, that means if the two particles are one above the other, you can resolve if the distance is more than 700 nanometer as two separate entities. Otherwise, it was considered as a spheroidal structure. Okay, so then if you look at the STED, it was giving you a 60 to 70 nanometer, but it is again the wavelength dependent. And then the SIM was also wavelength dependent. It was giving red was giving around 130, green was giving 110, and blue was 100. But that means you cannot restrict yourself to only one wavelength. You should be also be flexible to use multiple colors, and you should be able to maneuver over different technologies. That's why we call it as multimodal. If you are imaging with a wide field fluorescence microscope, you may not be knowing that immediately you need a super resolution. You should be able to observe some of the rare phenomena on your wide field fluorescence microscope, which is considered to be the gold standard even today because of sensitivity and speed. And at one point of time, you feel that like I'm getting some unique structures which I want to resolve. You should be able to switch over to confocal. Switch over to confocal, and then you see like wonderful images. You do optical sectioning, and you feel that like at a specific region of interest, you are seeing some important structure that needs to be resolved better than confocal microscope. You should be able to switch over to super resolution microscope. So multimodality was also one of the most important criteria for super resolution imaging, where people should have been able to switch from one technique to other technique as and when it is required. Second thing is there should not be any restriction in using the dyes. If I'm using a fluorescence microscope with a conventional wide field fluorescence microscope, without the need of changing the sample preparation, without the need of changing the dyes, so I should be able to take the same sample to confocal imaging and then super resolution. So that was one of the biggest demand in the industry, especially people who are working on spheroids, organoids, or people who are working on live cells. For fixed specimen, it was okay to go with any of these techniques because you can always choose to like have different dyes. But for live cell imaging, it was always a challenge to change the staining technique. To always to change from one platform to other platform. So these are some of the techniques that were currently being as we discussed. So if you look at this one, if you want speed as well as resolution, so then, so like probably the spinning disk based super resolution microscope can be a better advantage than any other technique that was giving you better spatial resolution. So this is just a comparison made. So here, if you see here, the single molecule localization microscope was giving an excellent resolution of 10 nanometer. STED was giving 30 nanometer. Structured illumination was giving 120 nanometer. We were okay with 120 nanometer, but we wanted a better speed. So that is achieved by super resolution confocal microscope from Evident. So now the number of images that are required to form an image, thousands of images has to be acquired to get a palm or storm image. One image for stimulated emission, but acquisition time will take several seconds. Sample damage is also one of the important criteria that we need to see. If you are acquiring tens and thousands of images, sample will naturally get damaged. Live cell as well is a challenge. Here also, because of the STED beam, you will be eliminating the sample with a heavy laser beam. Because of this one, sample toxicity, photo bleaching was heavy, and it used to take several seconds to compare. I mean, it was not a live cell friendly, like especially for high speed live cell imaging. Structural illumination was similar to where you were taking same sample without the need of any specialized sample preparation, but it used to take around 8, 9 to 12 images or 15 images. So the total time required to complete one image is seconds. Sample damage is lesser because compared to the thousands of images here, you will be only few images you are taking. So relatively lesser photo damage. And then restriction on fluorescent molecules. So there is a restriction. You cannot use all the dyes that you are currently using it for regular fluorescent microscope. Instead also needs a specific dye. Same didn't had it, but the limitation of speed is speed. It was giving 120 nanometer. So what is lacking here is you need 120 nanometer, but you should not have a sample damage. You should not have a restriction for using different dyes, but you should have a better speed. If you compare this one here, between structured illumination, which is a seconds, and here you are acquiring in milliseconds. That means each exposure is one image. So the advantage of spinning this confocal microscope with the super resolution achievement is you can achieve better speed at retaining the resolution of a conventional structured illumination system. How does it work? So I'll just switch over to different techniques. This is SIL. So what you do is there are several stages where you will achieve this super resolution. One is the conventional spinning disc confocal microscope, and then you have a dedicated hardware to collect the super resolution. You construct an image directly without the need of any software intervention. And then if you can take out the super resolution component and then reconstruct an image with the software in real time, so that will further improve the resolution and signal to noise. And finally, if you can further process post-acquisition, it should be giving you a resolution of 90 to 100. So there are three different stages where you will be achieving this, but they run in parallel, they run in real time. So how does a spinning disc confocal microscope looks like? So this is a conventional inverted fluorescence microscope. This is a Yokogawa spinning disc confocal microscope scan head with a scientific CMOS camera. This can be with a single camera or a dual camera. This Yokogawa scan head now comes with an additional component called SORA or super resolution by optical reassignment. So this will help you to switch from wide field to confocal and to super resolution. How does it work? So now you have a dual disc technology as we seen here. This is a micro lens on the excitation side. It will enhance the excitation efficiency. It will go and hit the specimen. Emission comes back. The emission is now reflected toward the camera, and camera collects the information in real time. But here, this is a conventional spinning disc confocal. How does it differ from SORA or super resolution? By optical reassignment. So the way in which your micro lens has concentrated the excitation efficiency, or in other words, narrow down the point spread function of your excitation light. So what Yokogawa did is they tried to implement a micro lens on the emission side also. Now the emission point spread function also has constricted. Now the point spread function or the resolution of the incoming point spread function, incoming light, is now narrowed down to 140 to 150 nanometer in real time. So what the purpose of concentrating the excitation light is now reused to concentrate the emission light into a narrow point, and that's how you get a better image. So that is done by SORA or super resolution by optical reassignment. How does it do? So initially, like when you have a sample, this is what you get, one area unit. This is what you collect, and the diameter will be 120 or 250 nanometer. So it doesn't mean that your sample or the collection, the point that you will collect does not have a smaller particles. It will definitely have, but we won't be able to resolve if the size of these structures are lesser than 250 nanometer. So it might have structures which are maybe 40 nanometer, 50 nanometer, 100 nanometer, or 120 nanometer, or 200. If it is 250 nanometer, we can resolve, but there are a lot of smaller structures that are unresolved here. These are the smaller structures. So what we do is, if we close the pinhole, or if we have a micro lens on the smaller, this one, it will try to position it, and then it will increase the center of gravity and increase the intensity, and thereby it collects more signals. Here, by having a micro lens on this side, it will enhance the point spread function. It will narrow down the point spread function. It collects more photons, and thereby you get a better signal to noise ratio and resolution. See the comparison between the conventional confocal microscope and resolution and the SORA. The resolution always improves here with the SORA. This is 0 nanometer, 50 nanometer, 100 nanometer, 150 nanometer. So like here, initially with the confocal with 1 area unit, it was more than 250 nanometer here. But here, when you are using SORA, you could come down to 150 to 140 nanometer. So we have a shift from 250 to 140 to 150 nanometer just by introducing a micro lens on the emission side with the SORA or super resolution by optical reassembly. But we didn't stop here because our challenge was to reach what a SIM can achieve, that is 100 to 120 nanometer. So what Olympus did is, so we tried to capitalize the spin index confocal microscope and used the similar technology as the structured illumination technology and collect the information. So in this case, what happened? We close the pinhole to 0.5 area unit. When you close it, so you get some of the information that are there inside this one. This is the information of the 1 area unit. When you close the pinhole to 0.5 area unit, you should be able to collect those information that are less than 250 nanometer. It could be 180, it could be 120, or it could be 100 nanometer. So when you close it to 0.5 area unit, so you will be able to collect. But since you close the pinhole, first of all, when you compare a wide field fluorescence microscope, it was bright because there was no optical sectioning. Signal was coming from different planes. We were getting a brighter signal. The moment we introduce the pinhole to 1 area unit, so most of the signal is lost because we were collecting the signal from only one optical slice. But now we are closing it further down to 0.5, so the signal is further lost. So though there was better resolution, the signal was insufficient for us to generate a better image. So if you look at this one, so the spatial frequency at 0.5 area unit was better than the spatial frequency of the 1 area unit. However, the contrast was very low. It is at this particular state, an algorithm picks up only this particular signal coming from the high frequency region. This is called cutoff frequency. Anything above this cutoff frequency, twice the cutoff frequency, is the domain where you have super resolution components of the 120 nanometer components. Here it is showing you the 250 nanometer. A software will pick up only these information and try to enhance the contrast and gives you an image which has got only the super resolution component. That's how it does it. So what Olympus super resolution or evident super resolution does is it will close the pinhole to 0.5 area unit, collect the super resolution component, discriminate the super resolution component from the conventional fluorescence imaging, which is 250 nanometer, reconstruct an image in real time, and this is in this zone. So here, this OSR zone is the super resolution zone. Software will pick up the signal from this OSR zone and reconstruct an image in real time. Look at this image here. This is a confocal at 1 area unit. This is what you are resolving, 250 nanometer. With SORA or super resolution optical reassignment, by having a micro lens on the emission side as well, you have further improved the resolution to 150 to 140 nanometer in real time. Now, when you introduce OSR or Olympus super resolution or evident true sight, so close the pinhole further to 0.5 area unit, collect the brightest signal from the SORA, and put a filter, software filter that picks up signal only from the super resolution domain, and now it gives you a resolution of 100 to 120 nanometer in real time. And this is not a deconvolution. This is a software filter that picks up the signal only from the super resolution domain of 100 to 120 nanometer, reconstruct an image. How do we evaluate it? So if you take a ergolite SIM structure, so this is actually a scale. When you keep it under the fluorescence microscope, see here, there is no distance between these two. This is only one single. As you move further toward the right side, you can see they separate. The distance between these two lines is around 360 nanometer, but here the distance between these two lines is 180 nanometer. The distance between these two is 120 nanometer. Suppose if I'm using a conventional confocal microscope, I will be resolving somewhere between 240 to 250 nanometer, where I can clearly see a dark line between these two, demarcating this line with this one, saying the distance between these two lines are 120 nanometer. But if you go to less than 180 nanometer, you won't be able to resolve anything with a conventional confocal microscope. See, that's what it is. See, you see single peak at 60 nanometer, 90 nanometer, 120 nanometer, 150 nanometer, but at 210 nanometer, you can see a dip here. That is the place where two lines are there. So that means a conventional confocal microscope can resolve at a resolution of 120 nanometer if you write a algorithm grid chart. Now, if you see what happens, if you are using a super resolution and SORA and OSR, you will be able to see a minor peak between these two and then a dip in this one showing that these two are separate lines. The distance between these two is 120 nanometer. Okay. Now, if you see, if you go further, if you use this one, you will be able to resolve up to 90 to 100 nanometer. So this is what you achieve by implementing super resolution by optical reassignment, SORA, and Olympus super resolution or evident true sight live, where it can selectively pick up the super resolution component by closing the pinhole to 0.5 area unit. In all these cases, we were not at all using only a software. It is a hardware and software approach. The SORA was completely a hardware approach. SORA plus OSR is close the pinhole with an appropriate hardware, use a high resolution objective, high numerical aperture objective, collect the super resolution component and real time reconstruct the image, just like any other SIM or structured illumination microscope does it. But in case of structured illumination microscope, you have to take 12 to 15 images at one go to construct one image, but here it is one image that construct here. But of late, you are getting a better software algorithm to do a deconvolution, and these deconvolutions are dedicated with a point spread function known of the super resolution. So if at all you are doing a deconvolution, what you are supposed to do is, I'll just show you this image. So this is a conventional SORA image, SORA and deconvolution. SORA means super resolution optical reassignment. See the structure here. But if I take the SORA image and then process it with Olympus super resolution module, an algorithm and hardware, you get better resolution. If you further take it to the deconvolution, now you can achieve up to 90 to 100 nanometer. So the first approach was SORA, 140 to 150 nanometer. Deconvol, you get 120 nanometer. SORA, you process it with the Olympus super resolution module, you get around 120 nanometer. This one, if you subject it to further deconvolution, you can go to 90 to 100 nanometer. These are fluorescence beads that are resolving here. Here, nothing can be resolved, partially resolved, same partially resolved, but deconvolution makes a very distinct structure. See this image, SORA and deconvolution, SORA, OSR and deconvolution. This gives a clear information that if you are using a Olympus super resolution along with SORA, it gives you enhanced resolution and it becomes a base for better deconvolution than directly deconvolving the SORA image. See here, if you see the frequency patterns here, there's a line drawn here. If you take a line profile of this is what you see here. And here you can see some dip here because it is slightly better. So and deconvolution, but SORA, Olympus super resolution and deconvolution gives you a better dip here, creating a clear-cut demarcation between the microtubules. This is again an image here. This is conventional confocal with SORA and deconvolution. So this is again seen against nuclei, zoom, and this is SORA, and this is SORA and OSR deconvolution. So with this, so what we have achieved is, initially we decided that we should have a better sensitivity and speed because this was one of the limitation of the conventional confocal microscope. Though confocal has given us an excellent resolution, excellent signal to noise ratio, optical sectioning capability, there was some limitation. Some of these limitations were listed earlier. One of the major limitations is speed. Second was phototoxicity. Third was the sensitivity. So because of this, so people have decided that we should have a better detector. And if it is if we can use a conventional camera which has got a better sensitivity quantum efficiency, so then you have to have multi-point excitation, switched over from a conventional point scan, single point excitation to a spinning disk confocal microscope where we used a NIPCO disk with a multi-point excitation. But NIPCO was not efficient enough in utilizing the laser because 70% of the light was being blocked by the inter pinhole regions. So in order to enhance the excitation efficiency, Yokogawa came out with a module called micro lens on the excitation side. Dual disk technology with a micro lens has helped us to greatly enhance the excitation efficiency. It has become a gold standard. but it was not addressing the requirement of a super resolution. Yokogawa came out with a new module called super resolution by optical reassignment by implementing a microlens on the emission side also. It has further reduced the point spread function or the PSF, or the resolution was improved to 140 to 150 nanometer. But the gold standard of the structured illumination was 100 to 120 nanometer. In order to achieve, Olympus came out with a module called SORA, where we introduced additional optics to reduce the pinhole to 0.5 area unit, collect the super resolution components in real time, process the super resolution component in real time, and then reconstruct an image in real time that gives you a real time super resolution with a frame rate of 100 frames per second, as opposed to the conventional sim based imaging that gives you a frame rate of 100 to 10 to 15 10 to 15 frames per second. Whenever you are going for structured illumination, the resolution of an image is also compromised. It will be only 512 by 512, whereas the SORA based system with the OSR gives you an opportunity to image at a resolution of more than 2 megapixel or 2K by 2K. That means finer structures can even be resolved without compromising the Nyquist criteria. So you acquired an image at a higher frame rate, better spatial resolution, better sensitivity with the evident super resolution microscope or OSR. However, if you are imaging, sorry, I think I just a minute. Give me 1 minute. I just want to show you one thing. Can you see this window? Hello.
Yeah, you are in this your first slide, sir.
Okay, just a. I need to show you. Actually. Okay. Can you see this window now?
Yes, sir.
Okay, see, this is some examples where one can do a live imaging also. See here, super resolution with live microtubule extensions. This is the live mitochondria image. And let me just show some other images. Just wanted to show some more live images. See this image. So this is a endoplasmic reticulum and mitochondria being imaged together with the super resolution by optical reassignment as well as OS. And see here, this is a conventional image where you see a wide field image, and this is the wide field image is deconvolved. No doubt it helps you to improve the resolution, but this is a super resolution, and this one is super resolution and deconvolution. Microtubules and the proteins can be easily, this one I have shown you. And the last one is if you have a thick tissue, how do we image? Because you want to have a super resolution on thicker tissues, because nowadays people are switching over from a monolayer cell to multi-layer cells. So if you are imaging a sample, so if you go deeper into the tissue, what happens is there is a phenomenon called spherical aberrations. The refractive index of a cover glass is 1.5, whereas your tissue is 1.4. Because of this refractive index mismatch, a spheroid structures will never be seen as spheroid, it will be an elongated structure. So in order to address this one, we came out with a new objective called silicon immersion objective. Earlier it was replaced by a water immersion objective, but water keeps on drying, and water refractive index still does not match with the refractive index of the cytoplasm. A silicon immersion oil was introduced, a new objective which helps us to match the refractive index of the tissue. The silicon immersion oil refractive index is 1.4, better than the refractive index of the water, lesser than the refractive index of oil, and it helps us to go deeper. Like this is fluorescence beads that are distributed at different depth of your specimen, imaged with silicon. See, it helps you to go deeper into the tissue. In this particular case, if you're using an oil immersion objective, you get a brighter spot at the just beneath the cover glass. For all silicon and water, as you go deeper, your sample gets elongated. And at 100 micron, an oil immersion objective gives you a very streaky image. That means it does not give you a proper 3D image. So silicon can even go deeper into the tissue. See, if you go to the water, even at 200 micron, like you have completely lost the information with water, silicon is still giving a better intensity. That means you can get a clear 3D image with a silicon immersion objective than the conventional oil immersion objective or the water immersion objective. Plus, silicon oil does not give you an autofluorescence. It does not dry. It does not change its viscosity with respect to temperature. That means it can be used with CO2 incubator with 37 degree or without CO2 incubator at lab temperature that is 22 degree. So silicon immersion objective is resistant to for all these chromatic aberrations. So there is a high possibility that you get a better, sharper image even at the deeper tissue. If you see this one, see this is a Purkinje cell labeled with GGFP. The upper surface is brighter, crisper, and as you go deeper, it comes with a built-in correction collar. Automated correction collar will help you to adjust the correction color, and you should still be able to get a sharper image even at the deepest position. It also gives you an option to do a 3D time-lapse image, where you should be able to do X, Y, Z, and 3. In this particular, say with a 500 milliseconds of exposure with 0.15 micron thickness, 41 slices were acquired for 2 minutes interval and 1 hour. So that means this will give you an option to image a 3D time-lapse image, because your 3D construction is more precise than the conventional oil immersion objective. This objective comes with a better working distance of 800 meters. So in conclusion, spinning the super resolution confocal microscope has helped us to achieve a better resolution, sensitivity, and speed. And it was further addressed by the SORA, which has helped us to achieve a better resolution of 140 to 150 nanometer. The SORA image was further taken forward with a additional hardware by the Olympus Super Resolution to achieve a 120 nanometer real time. And this image was further deconvolved to achieve a 90 to 100 nanometer in real time. So the spin-in super resolution has become a gold standard for live cell super resolution imaging compared to any of the existing super resolution microscope, which has got its own limitation for live cell super resolution. So with this, I conclude my presentation. If you have any questions, please feel free to ask. Thank you very much.
Thank you, sir. Thank you so much for such an insightful session. So, participants, please feel free to unmute yourself and answer the question. I think that is also fine, or you may drop it in the chat box on the side as well, whichever you prefer.
I am fine. I can take up the questions now.
Okay, sir.
Okay, it seems like there's no question.
Yes, sir. Or maybe we'll just wait for a minute.
Yeah.
Just a minute. Or is maybe anybody using evidence systems and they have any questions to ask? Maybe. So feel free to.
Yeah. So what you can do is you can like leave your email ID, or like they can send you and you can collect these questions and you can send it across.
Sure, sir. I'll.
Okay, then thank you. Thank you very much.
Okay,
Sunita,
then.
should we?
Thank you, sir.
Okay,
Yes,
there
sir.
is a
Okay.
question in the chat box, no?
No, sir.
Okay.
I have just
Okay.
dropped the email ID in case
Oh,
anybody would want to
oh.
drop any question. Thank you so much, sir. Thank you,
Thank you
everyone.
very much. Thanks a lot.
Thank you.